Alright guys, welcome back. This is going to be your tutorial number 4, I believe, the relationship between chemistry and biology. So we're actually going to get into the science part of biology, so it'll probably start getting a little harder. These tutorials may get a little bit longer. I'm still only going to narrow down the things that you need to know, but I might need to do some background info. For these especially, if you have any trouble, do just message me or email me, and we'll talk about it a little bit more. Alright, so I'm just going to kind of scratch the surface with all of this. If you have any other interests, feel free to let me know. I'm going to start at page 4, skipping the introduction as always, and it just has you starting off by defining matter. Just remember, matter is anything that has mass. Alright, so if it has any kind of shape, it has any kind of form, it is going to be matter. Things that are not matter are energy. Energy does not take shape, does not take form, so those are a little bit different. Alright, so you really split up things into two different categories, energy and matter. So we're going to move on to slide 5. Where they define an atom and they just show you the structure. It's fairly simple. An atom just has parts. It has 3 main parts. You're going to have protons, neutrons, and electrons. Is that described on this page? No, it is not. Okay, so don't worry about the guy who figured that out. Let's find out. Okay, here. So on page 6, they're actually going to talk about the 3 different parts. So what I need you guys to remember is that in the center, you're going to have protons, protons, and they are positive charges. Alright, maybe I should use. I don't have a blue pen today because, I don't know, pencil doesn't show up. Alright, whatever, we're just going to use black pens. So they're positive charges, okay? And they're in this cluster with what are called neutrons. And neutrons have a neutral or no charge, okay? So they are no charge for neutrons. And then floating on the outside far, far away are little electrons. These are negative charges. Alright, and there could be a couple of them. We don't really know. There could be a couple of anything. So the point is, you're going to have this little cluster in the middle of protons and neutrons, and on the outside you're going to have electrons and electrons, right? You just have to memorize the charges. You should remember them. P for protons is P for positive, N for neutrons is N for neutral, and E, well, sorry, you're going to have to come up with your own thing for that. Electrons are just negative. Alright, so we're going to go ahead and move on. Let's check out number, that's funny. So they actually go over the mass of each of these particles on your page 6 there. They say protons are 1, neutrons are 1, and they say electrons have 0 mass. That's actually not entirely true. They do have a mass. It's ridiculously small, but I guess they don't need you to know. I guess we won't worry about it. I don't know if it'll come up, but they technically have a mass. It's 9.11 times 10 to the, it's like negative 31st. Alright, then there's kilograms. But generally electrons are accounted for, and they use this number here, which doesn't show up in your tutorial. I don't know if it'll come up. It probably won't, so you can probably ignore this. In any case, electrons have a negligible mass. It's like a super small number. So like that negative 31 means that this number is really like 0.0000000000000. I don't know, a whole lot of zeros, and then finally 911. So it's not really all that big, so you can kind of ignore it. What they really mean is electrons have a negligible or a really, really tiny mass to where we're not concerned about. Alright, let's move on to page 7. That's a question for you. Good luck. Let's move on to 8. 8 shows you the periodic table, and we talk about isotopes. Okay, cool. So let's talk about, and I'm going to do this a little differently. We may end up covering a couple of things that are on the next couple pages, but that's okay. I don't want to use the back of this page. We're just going to use the front of this one. Let's see if I can't get this back. Is that right? Yeah. Okay, cool. So reading a periodic table of elements, you'll notice that you actually have several numbers on there. Most of them look like this. So let's pretend we're going to use, I should probably bring up a periodic table for this, but I'm going to use, I don't know, nickel as an example, just because I happen to know nickel, so this one will work. But you'll have some kind of abbreviation that represents your element, and then you're going to have a number up here. Nickel is 28, so it is the 28th element. Alright, and then you're going to have some other number down here. I actually don't, here, hold on, let me Google this. What's the mass of nickel? It's like 58.69. So then you'll have a mass number down here, 58.69, and Yeah, that's about it. So what this number means is, or what this whole thing means is, this is your element. That's nickel. This is your atomic number, or the number of protons. You can generally assume that your number of protons or your number of neutrons will be the same for periodic elements, but there is something called an isotope. So isotopes are elements with weird numbers of neutrons, with, I don't know, weird numbers of neutrons. So let's pretend we're dealing with nickel again, or whatever. Actually, let's go with something you guys are used to, like oxygen. You guys know what oxygen is, right? Oxygen has an atomic number of 16, which normally means that oxygen is going to be, or I'm sorry, no it doesn't. Just kidding. It has a mass of 16. Oxygen. Yeah, okay, my bad. So its atomic number is 8 and its mass is roughly 16. It's like 15.9, but we're going to use 16 here. So when you deal with oxygen, what this atomic number means is it has 8 protons and 8 neutrons. And I told you guys earlier with protons and neutrons, each of these are equal to 1. So to find their mass, you just have to take 8 plus 8, which gives you that 16. Okay? But the one problem with that, where it's not an exact science, is because we have things called isotopes. So going back to these isotopes, they're elements with weird numbers of neutrons. Okay? So that would be like an oxygen. It still has an atomic number of 8. Atomic number never changes. But for whatever reason, its mass number would not be 15.99. It's not 6. It's not 16. It's like 14 or something like that. And you know that 8 plus 8 equals 16, so there must not be 8 neutrons. It has 8 protons. It always has however many its atomic number is. Your atomic number defines your element. So if this ever changes, it's become a different element. So we have protons, and then this must mean that we have roughly 6 neutrons. This is a weird number of neutrons. Therefore, this is not a regular oxygen. This is what's called an isotope. Okay, so isotopes have weird numbers of neutrons. Anyway, that's how to kind of read these things. So I'm going to go back to the tutorial, which will probably tell me what I'm supposed to do. Alright, so where's my tutorial? I lost it. Okay, sorry about that, guys. So let's go ahead and move on to page 9 so I can see more of what they want me to show you guys. We just talked about isotopes, so page 9 is covering isotopes again. I told you they just have different neutrons. Okay? Oh, there's another way you're going to see your atomic numbers and elements written. So let's say I have, I don't know any of these off the top of my head. Okay, we'll talk about it if I see them on the tutorial. Right now I don't see any, so we're not going to worry about it too much. Alright, I guess just to read over this a little bit better, you'll notice that you have things like, on page 10, they have a picture of a carbon. So it goes 6, C, carbon, and then 12. This is called a carbon 12. What that means is it has 6 protons, and then you look at the mass, it's 12, so 12 minus 6 is 6 neutrons. This one is a regular element because it has 6 and 6. But you'll notice in your question it asks you which isotope has 6 electrons, 6 protons, and 7 neutrons. So instead of 6 plus 6, we want to know which one has 7 neutrons. So what's 6 plus 7? Yep, you guessed it, it's 13. So you're going to pick non-radioactive 13 carbon. So that's carbon 13. Okay, so carbon has the most common isotope. You see a lot of them in nature, so you'll come across carbon as an isotope example a lot, but you really could have anything. In any case, just remember it has weird numbers of neutrons, and remember how to add and subtract. As long as you can add and subtract small numbers, you'll be okay. Alright. We're going to talk about chemical compounds and the different kinds of bonds now. So, you can have all sorts of bonds, and bonds will do all sorts of things. I'm going to label out the keywords, and I'm going to highlight 2 kinds of bonds. I don't really know if you're going to get more during the rest of this tutorial, in which case I'll just go back to this page, I'll save a little room, and we'll add them all up to this page if I see more. But I'm going to go over two of them right now. Ionic bonding and covalent bonding. So the words I want you to focus on are, first off, the word ion. Ion just means a charged particle. So if your whole thing is positive or negative, it's an ion. Covalent, I want you to worry about the word co. Valence we'll talk about later. That's actually an important word, but we're going to focus on co. Co means together, right? So co, like cooperative or cohesive. That's probably a bad example to use, but that's okay. You get the idea. It's co. Co means together. Cooperative, cooperating, coalition. Also bad word. I really should pick easier words. I don't know what's wrong with me. So anyway, covalent means together. All right. So let's talk about the difference between the two and some of the key words. With ionic, you're going to see words like gives, accepts, and donates. For those of you that took physical science very recently, this might look really familiar to you. Or crystals. So ionic bonds often create crystals. Alright, so gives, accepts, donates, or crystals. For covalent bonding, you're going to see the word shared. That's almost everything you're going to see. Like, that's the one thing you need to know. So with an ionic bond, electrons are given away. They're accepted or they're donated. And then you form a crystal. So one ionic bond that everybody's really used to, and it shows up in your tutorial on page 11 here, is NaCl, or sodium chloride. All this really is table salt. So that's salt. Okay? And you guys know what salt is. It is crystals. Like, you know, you can take it, you can crush it up and put it in food, whatever. You guys know what salt is. That is the first example of an ionic bond. What happens is that an electron is given over here, and then you create this ionic bond, which is your table salt. You know, nothing special about it. You're really just looking for these words. Creates crystals. All right. Covalent bonds are a little bit different. The most common one that you guys are probably used to is H2O. Most of you guys know this is just going to be water. That is a covalent bond. It is also a polar bond, but we're not talking about that yet, I don't think. So I'm going to skip that for now. But H2O is probably the most prominent covalent bond, and the idea is that instead of NaCl, so with NaCl, that's kind of strange. Your tutorial does something kind of unusual here, so I'm not going to worry about bond strength right now. It's very unusual. In any case, you have a positively charged sodium and a chlorine ion here, and they'll mix together with the covalent bonds. What happens is that your oxygen will bond to your H's. Looks like this. And you've all seen this figure like that. And these bonds keep these hydrogens real close to the oxygen. When sodium and chlorine bond together, they are bonded just like with that. But the one thing that you have very different in ionic bonding is that this Na and the Cl kind of go off their separate ways. They're always bonded together in that one of them has one more electron, one of them has one less, but they can be really, really far apart. Doesn't really matter with ionic bonding because they're literally giving it away. There's no need for them to stay right next to each other. So really, this chlorine can be like, ooh, you guys can't see that. It's like all the way down here. It's completely okay. It's still a bond. It's just, you know, less prominent. Let's see. Page 12 looks like, okay, they use carbon dioxide as their bond. I use water. Whatever. Doesn't really matter. But just remember that covalent bonds are slightly stronger than ionic bonds. Sort of. Ionic bonds are really easily broken apart in some cases. Like, you guys have seen salt dissolve and that kind of thing. Like, you know, it's pretty easy to break them apart. Kind of. But there are different factors that cause that. Covalent bonds, generally, to break them apart, you'll have to electrocute them. It's kind of a big deal. So, doesn't really matter. We're going to move on to page 13. That involves a question, so I'll leave that to you guys. 14. Now, This is actually going to be an unusual section because honestly I learned it a little bit differently and there are some questions that I don't really understand. But here are solutions, suspensions, you can see that, colloids, I think you guys can see that. Alright guys, sorry for the abrupt cut in this video, but I had a little trouble with the tutorial a second ago, so we're going to retry this, and we're going to start again with our solutions, suspensions, and colloids. I'm going to edit these two together, and hopefully this flows properly, but I have a feeling that you're going to have this really weird abrupt jump. I do apologize for that ahead of time. Alright, so let's talk about solutions first. Solutions are going to be things that I can dissolve in each other, things that when I mix them together, they create a homogeneous mixture. If you guys remember what that means. So in homogeneous mixtures, everything, wow, that's an H, guys. A homogeneous mixture is going to have everything look the same. So like when you dissolve salt in water and you stir it up, all of the water looks the same. You know, it's pretty clear. Same with sugar and water. If you mix, Kool-Aid and water, it looks blue, obviously, but it's all uniform and that kind of thing. All right, so that's a big deal for solutions. Next, solutions are cut into two different things: solutes and solvents. The difference is fairly simple. Solutes are less of, solvents are more of. So whatever you have a whole lot of, that's your solvent. Whatever you have less of, those are your solutes. Okay? So this would be an example kind of like salt and water, like we said earlier. So here's your cup, and here's your salt. Okay, so you'll notice I've made some dots at the very bottom of this beaker. This is salt. And then here's your water. Okay, so like the rest of the beaker is filled up with water. So that's all water. Okay, water. Here we have to take a look at this, and you have to be able to figure out which one is a solute, which one's a solvent. You might already have an idea. Solutes, I told you there are less of, so you would assume that it's going to be that's going to be the salt. And your solvents are going to be your water. Alright, so solvents are your water. It's really simple, just which one's less, which one's more. Again, remember solutions are homogeneous, so they look the same all over. I drew the salt at the bottom like this, but really the salt should be dissolved in the water. I just don't know how to draw dissolved salt, if that makes any sense. It just is kind of hard to draw. There's a video in your tutorial which does it for you. It might be better to watch the video on page 16 rather than just look at my drawings. But if it makes sense to you, all good. By the way, all these are really just mixtures. So every one of these things that we're going to describe are three different types of mixtures. Solutions, the thing is, when I dissolve it all, it normally looks the same. Like, water dissolves salt, looks clear. Water dissolves Kool-Aid, it changes color, but it's still clear. It's a very clear liquid, right? It just happens to have some kind of dye or color to it, but it's a very crisp, same color liquid. So the idea is that whatever the liquid is, it's going to be the same no matter what. On the other hand, with suspensions are going to have suspended particles. So I can't use salt and water for this example because it doesn't create this cloudy look. But the idea of a suspension is that it will have a cloudy or dirty look, I guess. So if I take a cup and I put, water in it, just like always, but we also add, I don't know, dirt or something like that. Dirt's kind of a bad example, but if I put flour, you guys ever looked at flour in water? Or maybe if you've cooked pasta water, sort of. In any case, you see, like, you guys might not, dirt's probably a better example. So when you put dirt in water and you stir it all up, you get a bunch of particles all over the place, right? And it just looks like dirty water. When you spin it around, you can see the dirt clearly in it. What that means is that they are suspended in the water, or you can see the difference. So this one is not homogeneous. You can see this. So in salt water, you really can't tell. You might, because also salt water is very, very dirty. But if you just take like a glass of water and a tiny bit of salt, and you really take the time to dissolve it, or you heat it up and all that jazz, you're not going to see any of that. But if you take, pond water or something like that, you can heat it up all you want. It's still going to look dirty. It's still going to look like pond water. All right. So unless you sift out all the stuff, pond water just has that murky, dirty look. And that is what a suspension is. Colloids are generally kind of like gels. So if you think of like Jello or I think candle wax could probably be a colloid. Jello, other things that are jelly like. I don't know why I can't think of jelly. Oh, fat. When you let fat congeal, these are colloids. And the idea of this is they also have suspended particles, but they have really tiny suspended particles. And those tiny suspended particles do not move. So if you look at a clear jello, it's very, very clear. It's all the same color, much like a solution. But the problem is all of the particles are perfectly floating in it. They will not sink to the bottom. So if you let a suspension sit for a while, like really, really dirty water, and you just don't touch it, you end up with a bunch of dirt at the bottom of your little jar thing, right? But with a colloid, like if you let Jello sit, it's not like the bottom is going to suddenly start turning into dirt or anything like that. You just have Jello, like it just is. All right. So the differences are solutions. You're going to have a homogeneous look. It's all going to look the same. It is going to dissolve. All right. Suspensions, you have suspended particles. It looks dirty. You're not going to be able to keep that dirt up. It's going to eventually fall to the bottom. Colloids, you're definitely not going to be able to pull out these particles. Really, really tiny particles. It normally does look a little bit murky. So like Jello's a little bit harder to see through than like Kool-Aid, right? The reason is because it has a bunch of little particles that are just floating infinitely there that just don't fall. All right, so that is the difference between the three. Hopefully that made sense. Like I said, I learned it differently. I don't personally like learning them like this, but that should be pages 14, 15. On page 16, there is that video tutorial. That should help you. Oh, my bad. Colloids. They actually have good examples here. Marshmallows are colloids. That's kind of jelly-like. But they're less liquidy. Colloids are just less liquidy than the rest. So on page 18, you'll also see that they ask about red blood cells and how they float in blood plasma. You're going to look for an answer like suspension here. Now, I don't know how they expected you to know that. I know that because I've worked with blood before, but I don't really. This is not something you just know. But if you were to let blood sit around in a test tube without getting all thick, so like if you expose blood to the air and whatnot, it dries up really quickly. You guys know that. But if you just leave blood in a test tube, just a bunch of blood, you'll notice that there's stuff settling at the bottom of the bag. Well, that stuff is all the things from your blood. It's your blood cells. It's your skin cells, whatever else might be flowing around in your blood. It's all going to fall to the bottom of your bag. All right. So blood does settle out. Just remember the blood is a suspension for purposes of this test. Some people would argue otherwise. When blood sits out, it congeals and it becomes a colloid. But you get the idea. So those are the things we're going to go over for today. The main points that I want you to hit for your mastery test is just remember that electrons are negative, protons are positive, neutrons are neutral. So when you're dealing with that, so like if I lose a proton, so let's pretend we're dealing with, what's one thing I made you guys do? You guys dealt with nickel, right? So nickel has 8 protons, 8 electrons, right? So that's natural nickel. It just has 8 protons, 8 electrons. It neutralizes out. However, when you lose a proton, so let's say it only has 7 protons and 8 electrons still. It didn't lose any electrons. What happens now is that your charge is -1. If you lose an electron, now you have 8 protons, but you only have 7 electrons. In this case, your nickel is a +1. Alright, so just remember, if you start off with an even number of protons and electrons, so 7 to 7, and they're just going to go up or down. If you lose something, it goes down. So just add up your numbers. Protons are positive, electrons are negative, neutrons you don't even have to worry about, you don't have to count them. So if you lose like 50 neutrons, I don't know why you would, but pretend you did, it really would do nothing to your charge. Alright, what else? Oh, you're going to get a question on your mastery test that I really hated. It's going to ask you about a solution, and they're going to give you the options sand water, salt water, or flour water. The correct answer to that particular question is going to be think it's salt water. I don't know. Let me open up that mastery test real quick because yes. Okay. So a solution as defined in this mastery test is going to be salt water because remember salt dissolves in the water and it clears perfectly up. And then remember your difference between covalent and ionic. Just remember your keywords. Ionic gives, accepts, donates. Covalents are shared. And being able to read all of your atomic number stuff. So that was this entire page of material where we were just reading the atomic numbers and whatnot. I think you guys are good. I know I went through that kind of fast, but I wanted to keep these videos short even though we're actually getting into the science of things. Message me if you have any questions and let me know if you're having trouble with the mastery test. There's no need for you to take a mastery test like 50 times. Now that we're getting in the real science of things, if you ever have trouble with a mastery test, you've taken it once or twice, you've gone through the tutorials, you watch the videos, and they just don't make sense, talk to me about it. I probably won't make you do it, alright? We'll probably just talk about it and work through it, and it'll be okay. Alright, so don't stress over anything. Call or message or email me if you need anything at all. Other than that, thanks for watching, and I'll see you guys next video.